Now let's see one example of a high resolution Nmr spectrum. So this molecule has been given to you. We're just going to see the similarities between what we have learned and the Nmr for now. So here I have these three hydrogens, these three CH3 actually. These are in the same chemical environment. So they are attached to a carbon, attached to a CH2, etc. The two hydrogen here, they are in the same environment. They are attached to a CH3. They are attached to carbon bonded to free CH3 and a carbon bonded to O and CH3. And these three hydrogen, they are also in the same chemical environment. Now, when we look at these hydrogens, so we have 9 hydrogen in the same chemical environment. Here we have 2 hydrogen in the same chemical environment, and here we have 3 hydrogen in the same chemical environment. This is going to give us the intensities of the peaks. So how many hydrogen we have gives us the intensity. Now let's see the number of hydrogens on the adjacent carbon. So if we look at this carbon, these protons, so these three, the adjacent carbon is here. So if we look at how many adjacent hydrogen these have, so this adjacent carbon is attached to no hydrogen. So these have 0 hydrogen on the adjacent carbon. If we look at this one, so the adjacent carbon is here, so there's no proton attached to this one. Another adjacent carbon is here, so there's again no proton attached to this one. So here you have 0 adjacent hydrogen. If we look at this one here, these protons, the adjacent carbon is here, and this one has no hydrogen again. So here again you have 0 hydrogen on the adjacent carbon. Now, since all of them have no adjacent hydrogen or no hydrogen on the adjacent carbon, all of these will give rise to singlets, which means that you're going to have 3 peaks. Because we have 3 environments, the 3 peaks are going to be in the ratio 9:2:3, and these 3 peaks are all going to be singlets because all of them have 0 hydrogen on the adjacent carbon. And if we look at the Nmr, this is what we observe. So 1, 2, 3, 3 peaks in the ratio 2:3:9. So 2:3:9. The ratio do not need to be in the same order as what we see in the structure. So as long as you see the numbers 2, 3, 9, it's okay. And you see that you have all of them being singlets. Now, if you verify the data booklet, you're going to see that chemical shift value around 1, this is due to CH3. And around 2, this is due to CH2. And here you have the CH3 peak that has shifted downfield because it is attached to the electronegative oxygen. Let's see another example. So this is our structure. And it's 1,1,2-trichloroethane. So here we complete the structure. So here actually we're just confirming the Nmr spectrum with respect to the structure. Here's the detailed explanation. Let's see a third spectrum. So here we're going to see the effect of electronegative elements on chemical shift values. So normally we don't trust the chemical shift values that are in the data booklet because depending on what the protons are attached to, the chemical shift values can change slightly. It can go downfield a bit if it is attached to an electronegative atom. So let's consider the molecule C4H8O2. The spectrum is shown. So the first thing before trying to deduce any structure is to find the IHD. So it has an IHD of 1, and this can be interpreted by it having one double bond in the structure. And when we see this, it has 2 oxygen. So most probably there should be a C double bond O. So either it's a carboxylic acid or maybe an ester. That's also possible. Right? Now we can start interpreting the NMR. So also there is an IR peak at C double bond O, so it confirms either of these 2. Now let's see the NMR spectrum. We have 3 peaks. So we have hydrogen in 3 different environments. So let's see here. Chemical shift value, which is around 1.1 ppm. Here you have 3 protons. So intensity 3 means there's 3 protons. And you see it splits into a triplet, which means that it has 2 adjacent. So it has a carbon with 2 adjacent hydrogen, 2 neighboring hydrogens. So because we have 3 protons, so most probably it's a CH3, and 2 adjacent hydrogen, most probably it's attached to a CH2. So it's this peak. Then we have 1 chemical shift, which is around 2.4 ppm. And here you have 2 protons. And these 2 protons, the peak splits into a quartet. So 2 protons with 3 adjacent hydrogen. So CH2, 2 protons adjacent to a CH3. So 3 adjacent hydrogen. And we have 1 peak, which is around 3.6 ppm. And this has intensity of 3, so there's 3 protons, and it's a singlet, so therefore it has no adjacent protons. So means that it's a CH3 maybe which is bonded to a CO, or a CH3 which is bonded to an oxygen. So here we can confirm that there is no COOH. So this has been eliminated, because if there was a COOH, we would have 1 peak, a singlet, with an intensity of 1, but there is nothing as such. So we can confirm that the structure is CH3, CH2, and then you can have here, and then CH3. Or it could also be CH3, CH2, COO, CH3. These 2 structures are possible.